so we can zoom all the way down and see streets, you know, and cars and stuff. It's just, you know, it's a lot of data. That's a lot of data. But the touch table is designed to be a collaborative tool. So anybody who has another touch table, not connected. So when I move this, it moves there in real time. So I can zoom in here, and it zooms in there. So this computer could be in China, and we could be here in Mexico. We could do the same thing.
So basically, here you have a touch table here, and then the data itself should be generated from the other sources. Right?
Mm-hmm. So we have, in this scenario with the touch table, you need the same data on this computer and the same data on the other computers. So this could be applied around the world to help other nations identify, even before they know it, when their crops are going to be stressed. So you can say, hey, you know, we're working together in partnership. This is what we see. You know, is there any way we can get some more irrigation here, or we can get some water resources or things like that to help with the crops? So you can see all the beautiful vegetation and growth in the Nile River here, and then all this other area, which is a lot of desert. Exactly. So the other thing that we're seeing in the changing climate is precipitation trends. So what's happening is that we're seeing more rain falling in heavier downpours, which actually means more flood potential. And so that's what this particular image is showing. It's showing the increase in the number of days with heavy precipitation between 1958 and 2007. So in the dark areas here, 51 to 60%. We've seen an increase in the number of heavy precipitation events, which really means we're seeing heavier downpours and more floods in this area. And sometimes in the winter in the mid-Atlantic, more snowstorms because we're seeing storms come up the coast. See the river here, but you can see the flooding, and I can draw this. You can see the flooded areas here. Farmland. This is the river. And so we can zoom in and pan around. So any access to higher resolution data and imagery we can put on here. And what we see is when we talk about things like sea level rise, we can bring those two together, and that's what this is doing. We're seeing an increase in population. We can zoom in, and we can see what happens if the sea rises 1 meter. Where does it flood? So let me go back here for a second. I'm going to do a swipe and take off the sea level rise. Let me take off. This is 1 meter of sea level rise. I want to take off the population. There we go. So we can zoom down into South Florida, and we can see the impact of a 1 meter sea level rise in South Florida. That's not very good. You know, many people think with maybe the sea level rises, so the streets are wet, we can ride around in the cars, so what? No, when the sea level rises 1 meter, you're impacting infrastructure. You're impacting your waste, your water treatment facilities, and all that sort of stuff. So these areas become uninhabitable. And you know, in some cases where the sea level rises, the sea level falls in other areas as well. So when you think of sea level rise right now, but you know, you look at places all around the world. You know, let's you know, Bangladesh, 1 meter sea level rise, you'll displace 25 million people. So this is all very very important to understand what the impacts are of sea level rise. Africa, South America. You know, we can go and we have it. You can see the blue outline. Now, what if we went into, you know, Mid-Atlantic area, Washington DC here. This is in the Chesapeake Bay. It's called the Blackwater Wildlife Refuge area, where it's a bird sanctuary. This is the coastal area of coastal Maryland. It's a big vacation spot. You can see it, all of these are buildings, kind of like Cancun. You know, this is the hotel district. But in a sea level rise scenario, it's going to be quite impacted. And if we just go down here to Norfolk, Virginia, it's a big, big area that's susceptible. Here's Norfolk, and here. You know, all these people that live in here, you know, will be impacted. That's a 2 meter rise, and we have a 3 meter rise. So you can see the power of visualization. When the temperature gets over 100 degrees, it really puts an incredible stress on the body. And so we can take a look in these various scenarios of the number of days over 100 and how the public really thinks what's happening. We can really look at population density. You know, around the world, what has the population done? And you can see all around this population where people live, we have another problem, and that's the stagnation of air. You know, so where we have population centers and we have more pollution being emitted, we have air stagnation that's happening. Higher temperatures are associated with higher air masses, high pressure system. The other thing that we're looking at is the amount of clouds in the atmosphere, because in a warming environment we have more humidity in the air and we see more clouds develop. And that's kind of being confirmed, because when we have more clouds we have heavier downpours, and it's all pointing towards the changing environment and some of the things that we're seeing. This is total cloud fraction around the world, and the bluer areas show the cloudier areas. Lighter areas are a little, I'm sorry, it's the other way around. The lighter areas are more cloudy, and the dark areas are less cloudy. And as we use observation systems, satellites that are orbiting the Earth, we can put together trends over the course of a longer period of time and then make comparisons. Are we more cloudy? Are we less cloudy? Are we getting more drought in areas where we don't need it, or less drought? And so what we're also able to do is we're also able to take a look at areas like Alaska. You know, when infrared radiation from the sun comes in, it's we get a certain amount that's reflected out. Clouds play a big role in reflecting solar radiation back out. So as the Earth changes, we get different levels of absorption and areas of refraction and reflection. And agencies like the Department of Energy, the Atmospheric Radiation Measurement Division, is trying to measure more accurately cloud. You know, they're made of ice crystals. So when there are more cirrus clouds, it reflects more radiation back out into space. So we need to understand cirrus clouds and how cirrus clouds are impacted by this change, and also how cirrus clouds are parameterized in climate models. So climate models can become more accurate as we go out further. So that's what's happening there. And we also have, NOAA has observation facilities that are co-located in these. This is the kind of technology that we think can really help to tell the story of what's happening. And I mentioned before, but we have some new folks in the room, that this is a collaboration technology. So it's running off this PC here. This PC is a different one that's hooked in through the internet to collaborate with this one. And it's being projected on the wall over here. So it's two different computers. I have this one here and I can move, and then that computer is moving in real time. It's not a projection of this computer. It's not a projection. So this computer could be in Africa. It could be in China. You know, we could be collaborating through the internet. And dive right in and go to Cancun, Cozumel, Hotel District. Ooh, maybe Cancun Meste?
Yeah, maybe.
Right there? Close? Greenland is a fine island nation of ice here. If all the ice melted on Greenland, it would be a 23 to 27 foot rise in sea level. But it's not likely that we'll see everything melt. In this area, because of the ice melting, are more conducive to supporting the life of those little krill. So what do the krill, what do? They go from here up in here. But the whales don't know that. The whales come up here looking for food. They're like, yo, where's my food? But they can't find it. So they swim back down here to spawn, and what scientists are noticing is that when the whales get down here to spawn, they look emaciated. What's happening here is that we're seeing a change in the amount of snow cover. Over a longer term, the snow cover is coming down and lasting less. So we're seeing fewer of the ocean is showing that we're seeing more heat gathered in the ocean. And you can think of heat in the ocean as sort of like an energizer battery. You know, when a hurricane moves over the ocean with high heat content, it's like adding high test gasoline into your car. It gives it more efficient fuel to work and operate on. So that happened in Hurricane Katrina in 2005. The storm moved off of South Florida, hit the loop current. The loop current was 90 degrees. Boom. Went right from a Category 2 to a Category 5 hurricane. There's a little data glitch over Africa. But over here, generally it's kind of reddish, which shows you it's warmer. It's able to hold more heat. Rainfall patterns are taken by NASA's TRIM satellite. So it's satellite orbiting the Earth, looking at the rainfall and all that sort of stuff. And we can see different patterns of where heavier rainfall is falling in the tropics. And we can see this every day. And we can take a look at flooding that's going on along the river. And we can go in a little bit closer. And we can see how wide, the river has changed. As a matter of fact, we can measure it. We'd say, how far is it from there to there? 427 meters. So we can do a lot of measuring with this kind of tool as well. We can say, that's not usually that thick in this area. But if we go down here and say, you know what, the river here is usually pretty thin, but how wide is it here? 261 meters. So if you have satellite imagery, after you have a disaster or a flood, you can use the measurement tools to figure out how wide of an area there's flooding. How long is that road that you need to drive down to get to a certain location? And if you don't like meters, you can change it to kilometers. And if you don't like kilometers, you can change it to feet if you want to. So we can have the option of changing this all over. So that was a small little high-resolution satellite image in Brazil. And we can come out and look at this, these anomalies. Now this particular data set is called Sea Surface Height Anomaly. What does that mean? Well, when the ocean warms, it expands and it gets higher. So there's another satellite that orbits the Earth called Topex Poseidon, and it measures the height of the ocean. And what you're seeing here is the height of the ocean. Now keep in mind, when it's warmer, it's higher. When it's colder, it's lower. So we color-coded this to show warm temperaters as higher water, cooler temperatures as lower water. So all these different things here, it's kind of like what's going on here. What's happening here is that the Gulf Stream is coming around here, and it's going here, but when it comes up here at a fairly great speed, it spins. It creates little eddies. And these eddies of spinning water are warm, and they pull the warm ocean temperature up to the top. But when you pull warm ocean water up to the top, cold water replaces it. So you get warm, cold, warm, cold, warm, cold. Where you have these warm temperatures. And not only is it warm, but it's higher water. So this is a signature of a big El Nino. And when this develops, this changes global weather patterns because the jet stream in the atmosphere changes. There's more moisture in this area to entrain into developing weather systems. And that's what I showed earlier. In precipitable water, last year we had a big El Nino. And last year in the mid-Atlantic area of the United States, we had very big snowstorms. So let me take you back really quickly. And what the cloud fraction looked like, or total precipitable water. This is during an El Nino where there was much more moisture. You can see the moisture streaming up out of El Nino, coming right up into the east coast of the United States in February of this past year. When there's a La Nina, these water temperatures are cooler. And so we don't have as much moisture available above the cool ocean waters, so there's less likely of a chance that that moisture is going to get entrained up into weather systems. This is from the Extreme Ice Survey, James Baylog, who has put in cameras at 36 different glaciers around the world. These waves are probably 80 feet. We'll put it in reverse just to show you the incredible 2007.
How time lapse is that?
It's 1 day.
1 day.
Happened in 1 day. So this is the weak part, and as soon as that broke off, the equilibrium of this particular iceberg now has changed, and it's now looking to equalize itself. So what you see above is only 10% of the glacier that is the iceberg now below that. It's incredible. If it were to rise 1 meter, as we zoom down into New Orleans, what the implication could be. This is New Orleans right here. New Orleans is already up to 11 feet below sea level, and it's continuing to sink each and every year. But this is what's critical. All of the delta is underwater. And as you know, deltas and wetlands are critical in protecting the coastline from floods and wave action when storms come in. So this just, a 1 meter sea level rise is going to significantly impact the coastline. Take a look at South Florida. This is Miami, Florida. So the water of a 1 meter sea level rise will get into this area here, impacting hundreds of thousands of people. This satellite image is the night lights of the world. So where we're seeing the use and the desire and the need for energy is being reflected in lights being emitted that can be detected by satellites. So you can see the United States, Canada, Alaska. This is Fairbanks and Anchorage. We can go around the world to see Japan. Zoom in a little bit on Japan, because we can see some very dim lights right here off the coast. And this is some of the fishing fleets in Japan. They're out there at night. They have big booms with lights on them, and they're shining them down on the surface of the ocean so the fish get attracted to light, and they can scoop them right up with their nets. You can see South Korea, North Korea, the difference in the lights. You see China. You can see the Trans-Siberian Railway. All of these places and all of these population centers rely on energy. And many cities are built based on transportation routes. So you can see these dots that are all around the Trans-Siberian Railway because it's a key transportation area. Not many people living in Greenland. It's a big ice sheet, but there are some lights showing up in some of the small towns. So it's a fascinating world when you look at it. Thank you very much. So satellites help us to track weather systems. Satellites help us to understand the climate system. And what's important to understand is that the accuracy of our satellite observing systems is going up. It's increasing. It's getting more accurate and more accurate. And that's critical because as you talk about weather forecasting as compared to climate prediction, you need to have more accurate satellite measurements to have more accurate climate predictions. And so this is Hurricane Katrina in 2005, when Hurricane Katrina had 175 mile per hour winds. And the winds are blowing clockwise or counterclockwise around the center. 175 mile an hour winds right there. And what happens when you have a strong hurricane is it builds up a strong storm surge on the right side of the eye. And so as this storm is moving towards Louisiana, it's building up a big storm surge. And so what we're able to do is take forecast information from the National Hurricane Center and overlay that onto the satellite imagery so we can see where the storm is predicted to move. So it's predicted to move right here into southern Louisiana, and this is the cone of uncertainty. That's telling us that the hurricane is expected to move in this area somewhere, but we're not sure exactly where. Now, because of improvements in weather forecasting and improvements in satellite imagery, we can see from this graph right here, this is the improvement in hurricane forecast. The 72-hour forecast is just as accurate today as the 24-hour forecast was in 1970. That's really important. There's a reason for that. And that reason is because we have more global observations. We have more satellites. We have more observations on the ground, all going into computer models that are predicting what's happening. We can also, with digital elevation models, and try to determine who is most vulnerable to things like sea level rise, who's most vulnerable to storm surge. And so this is a digital elevation model of New Orleans in Louisiana. Digital elevation model means how high or how low is something, and anywhere you see in blue here is below sea level. Anywhere from 1 foot to 11 feet below sea level. So this is not a good place to be if a flood is coming, because you basically live in a bowl. The water comes in, you have to pump it out. But you can also see areas that are above sea level. So to protect the city, they've built levees. And you can see this orange and red. And I can zoom in here a little bit closer. Orange and red around the river, the Mississippi River, to keep the floods out. So if the river rises, these hills are going to keep the river contained. supposedly. This right here is the Superdome in New Orleans. And what I want to do is show you higher resolution imagery. This is 1 meter resolution data. So for every pixel, for every little square on the screen, it's 1 meter, 3 feet. So you can see these neighborhoods. This is the lower 9th Ward, and this is another neighborhood right next to the lower 9th Ward, another area of the New Orleans, and you can see the canals here. So what I want to do, I can take you close. You can see the individual houses. You can see the road. You can see the bridges. And this is an area that was weak during Hurricane Katrina. The storm surge came up. The winds were strong. And there was a barge sitting right here that drifted, got pushed away from its mooring, and it created a hole in the levee. And this is what it looked like when the levee broke. So the levee broke, 18 feet of water came rushing into the lower 9th Ward. So this is all flooded. As a matter of fact, the water was so strong, it washed these houses inland. Move them all. See the houses that are right here? It pushed them all back against these houses here. So you can see the pile of houses that are just thrown together. The other interesting thing is the water is going out of the lower 9th Ward. You see it rushing out? That's because the tide is going down in the Gulf of Mexico. When the tide came back in, the water went right back in. Because this area is below sea level, this became part of the Gulf of Mexico when you had that kind of flooding. This is also an example of the Superdome. You can zoom in a little bit closer here. And when they had a lot of people evacuated at the Superdome, what they wanted to do is bring in buses to get those people out of New Orleans before the storm hit. So they brought in lots of buses to evacuate people. Well, this is what happened to the Superdome. And here are the buses lined up to evacuate people. But they were a little too late. Some of these buses are underwater, so they never got to get the people out. So we can see all sorts of applications for satellite imagery. And this satellite imagery can help make better decisions in disasters. It can help make better decisions for mitigation activities. It can help make better decisions for adaptation. Welcome. Hello. And so what we're able to do is to help with emergency management response or planning for future situations. So here's what's happening with Hurricane Ike. This is Hurricane Ike in rapid scan satellite imagery. So remember, we have a satellite that's orbiting 22,000 miles up in space, and it can look down and take an image every minute if we want. If the National Weather Service and NOAA put the satellite into that mode, it can take an image every minute, so you can see things spinning around rapidly. This is a very impressive capability, so we can see storms developing rapidly and whether or not hurricanes are developing rapidly. It's called rapid intensification. This is an example of Hurricane Ike when it was just offshore of the state of Texas. And this is Doppler weather radar data. The surface of the water is being disturbed by the wind. It's called surface roughness. And what's amazing with this image is this is radar data. Let me take away that radar data and show you what it looks like on the surface of the Gulf of Mexico. This is the surface of the Gulf of Mexico. It's reflecting the eye of the storm because the winds are blowing around really strong, disturbing the surface of the water, and you can see the Gulf of Mexico and the eye of the hurricane. So here's the radar data, and here is the surface. And I want to show you something else that's pretty extraordinary as well. This data itself is showing where the water is. So this is Galveston Island, and this is Boulevard Peninsula. On a normal day, this is what the coastline should look like. On a regular day with no storm, sea levels, no problem. But during Hurricane Ike, look what happens. The entire island of Galveston is underwater, except for a little spot right there. And the Boulevard Peninsula, totally underwater. They lost 600 homes in Hurricane Ike because of the storm surge that came in. So you can see that from satellite imagery and satellite data. And it's quite extraordinary. And this is combining European satellite imagery and US radar data and also Landsat imagery from the US as well. What else is important with the landfalling storm is how big a storm surge are you going to get. And this is output from what's called the slosh model, showing when Hurricane Ike comes up into the coastline, what's going to happen with the storm surge. And you can see the colors here. Yellow is 10 to 15 feet, 20 to 25 feet in the orange. So they were thinking about possibly massive storm surges coming into places like Port Arthur in Texas, where a lot of people live. So they have to make decisions. Do we need to evacuate Port Arthur? And we need as much advanced warning as possible. We can also dive in here and show you the effects with satellite imagery of a landfalling hurricane. When a hurricane comes inland and washes salt water in, the vegetation does not like that. So we had a huge impact with vegetation when Hurricane Ike made landfall. In this false color image, what we're showing is we're taking all the healthy vegetation and coloring it red. So wherever you see red, that's healthy vegetation, it's good. But after Ike made landfall and the storm surge came in, this is what it looked like. All that vegetation was destroyed, except for one little spot right here called High Island. And it was high enough where the salt water didn't flood it and didn't kill that vegetation. So this is before Ike, after Ike. And in some cases it takes a long time for this vegetation to regenerate. And it weakens this whole area. The vegetation here was weakened. It's not as red, see? But here, it's much weaker. The ability for these trees and the ability for these plants to absorb CO2 is lowered. So these plants are nowhere near as efficient in capturing CO2. I want to take you over to Russia. How many of you remember hearing about the Russian fires this past summer? We had a lot of fires in Russia. What this is showing is the temperature anomalies in Russia. It was a heat wave. They had temperatures of 20 to 30 degrees higher than average. That's one ingredient. The second ingredient, they had a drought. This imagery is normalized vegetation index imagery. So we can look at all these forests and all these plants that are growing. Welcome, come on in. And we can see which ones are stressed because they don't have enough moisture. The process of photosynthesis is shutting down because they don't have enough water and moisture. So they're under a massive drought. That's the second ingredient. A big heat wave, massive drought. The third ingredient, low humidity, and that's a cause for wildfires. So they had some thunderstorms that formed, lightning strikes the dry trees, breaks it up into fire, and these fires, as you can see right here, are burning. And they're burning rapidly and spreading rapidly, spreading smoke throughout all of Russia, just about. And when the smoke happened, visibility goes way down, and you don't see very clearly. People were wearing masks. This is Moscow. You see the visibility of people walking around. That is not healthy. Anybody with respiratory problems, young people, older people, big problems breathing. And several people, they lost several hundred people because of health issues, because of the fires from respiratory problems.
2,000 homes were
Okay. These fires also affected the people's homes. 2,000 homes were destroyed in these fires. And you can see what's happening with the upper level winds. The jet stream blowing like this. So whenever you have these fires, the smoke is carried in the jet stream on that conveyor belt of winds. And where you have high pressure system, if you have a high pressure system here, the winds are calm, so it traps the smoke at low levels and keeps it around. So when you can predict these kind of things coming together, you can let everyone know that there's a high chance of forest fires and a high chance of significant health issues should fires develop. This is the emissions of carbon monoxide because of the fires. Because of the Russian fires this year, I think it was, what was the amount of carbon monoxide released was more than any carbon monoxide that Europe has, the European area has released in a number of years because the fires were so intense. So this is an example of monitoring the releases here and how dangerous carbon monoxide is. You can see it from satellite. Over here shows nitrogen dioxide. This is the release of nitrogen dioxide because of fires around the world. You can see in the United States from burning, in South America from burning, Europe, India, China, releasing all of these carbon monoxide chemicals into the atmosphere. And carbon monoxide nitrogen dioxide is an irritant. You know, it really makes your eyes burn, and you can't spend much time outside when you have that around. So what I want to dive into now using satellite imagery is an example of a glacier that collapsed and carved its way down a river and killed 125 people in Russia. This is called the Colca Glacier. So you can see what it looks like right here. This is the Colca Glacier. You can zoom in. You can see what it looks like. About this much of the Colca Glacier broke off. And it was lubricated on the bottom because there was a lot of melting going on. And this whole glacier slid down the river at one time. So this is what it looked like. This is before, and you can also see it on the screen up here. And this is after. So you can see the glacier here is gone. It carved a huge area. Let me draw it for you. Oops. It increased the size of this river by a significant amount. And when it got down to here, all of the ice jammed up created a brand new lake. And you can see that when I do this swipe again. So you can see that the ice went down here, got jammed up, created a new lake, killed 125 people down the bottom. Why did the Colca Glacier break? There's melting going on and lubrication because there's more water that's melting underneath the glacier. So it gave it a surface that it could ride down and carve out huge areas where this river was, and still is. So here's a close-in picture of the ice and how it jammed up this area and created this whole new lake. I don't know what the name of it is. Maybe Colca. But these are, the lake was formed by all the debris that came down. A lot of these are trees too, probably in here as well. So now I want to take you out to a landslide in China that happened this year. And this landslide was due to heavier rain. And we can see the rain that's fallen from the NASA TRIM satellite. So we can move this around and see that there was a high area of rainfall during this particular month. And I want to dive in just a little bit closer so we can see in satellite imagery what happened with this landslide. As a matter of fact, it was cloudy and raining quite a bit. A hole opened up in the clouds. See, I can zoom out a little bit. See that hole in the clouds right over where the landslide happened, so we could dive in a little bit and see what the effects were. And this is a picture of the landslide as it came down right through this town in China. And it killed more than 1,200 people. So by looking at the vulnerability of hillsides, and there's some work being done at NASA right now to help to predict when landslides will happen based on the amount of rainfall. The TRIM data, the global rainfall data, is very important as an input into that model to predict where landslides might happen. So we can take higher resolution imagery and embed it into a global data set to show areas of importance in what's happening. There was also a massive flood in Pakistan this year. Remember? You probably remember hearing about that, where it displaced 20 million people. This is some of the data showing the rainfall in the Pakistan area. And what I want to do here is I want to dive into a sequence of images, an animation. Or is it on this? Oh, I have to do it on the file. There we go. But they had a massive amount of rain. So what I want to do is put this into motion and show you how the river expanded in the rain and how this cut a new channel around this river and affected 20 million people. You can see the river growing, expanding, and connecting right into here. So this whole area was just major floods. We can take you back and forth showing the sequence of imagery. There it is before the flood. No problem. Heavy rain, and this water just rushing down, affecting 20 million people. This sequence of imagery is over a 3-month period. It's not like the water came down and washed through in one day. 3 months. People had to move away from their homes, had to find a place to go. 20 million people.